Welcome everyone. Today, we'll explore the iron-carbon phase diagram, a fundamental tool in metallurgy. This diagram helps us understand how microstructures transform during thermal processing, which is critical for designing heat treatments and predicting material properties. The iron-carbon system is the backbone of steel and cast iron production. Understanding this diagram is essential for controlling phase transformations and achieving desired mechanical properties. The iron-carbon phase diagram is a fundamental tool in metallurgy, providing a roadmap for understanding how different phases of iron and steel form under varying temperatures and carbon concentrations. It is essential for predicting microstructures during heating and cooling processes, which directly influence mechanical properties such as strength, hardness, and ductility. Engineers and metallurgists rely on this diagram to design heat treatments like annealing, normalizing, and hardening, ensuring that materials meet specific performance requirements. By studying the diagram, one can anticipate phase transformations, optimize manufacturing processes, and tailor properties for applications ranging from construction to automotive and aerospace industries. Carbon content ranges and classification. Steel and cast iron differ mainly by carbon content. Steel and cast iron are both iron-carbon alloys, differentiated primarily by their carbon content. Steel typically contains up to about 2.1% carbon, while cast iron ranges from 2.1% to 4% carbon. This variation significantly affects microstructure and properties. Low-carbon steels, up to 0.3% C, are ductile and weldable. Medium-carbon steels, 0.3 to 0.6% carbon, offer balanced strength and toughness, and high-carbon steels, 0.6 to 2.1% carbon, are hard and wear-resistant. Cast irons, with higher carbon content, exhibit excellent castability and compressive strength but lower ductility. Understanding these classifications is crucial for selecting materials for specific engineering applications. Here's the annotated diagram. It maps temperature against carbon content, showing phase regions and critical points like eutectoid, eutectic, and paratectic. These points guide us in predicting phase changes during heating and cooling. The iron-carbon phase diagram maps temperature against carbon content, illustrating regions where different phases exist. Key features include the liquidus and solidus lines, which define melting and solidification boundaries, and critical points such as eutectoid, 0.76% carbon at 727 degrees Celsius, eutectic, 4.3% carbon at 1147 degrees Celsius, and paratectic, 0.16% carbon at 1493 degrees Celsius. These points mark transformations that occur during cooling or heating. The diagram also shows phase fields for ferrite, alpha, austenite, gamma, and cementite, Fe3C, as well as mixtures like perlite. Mastery of this diagram enables engineers to predict phase changes and design heat treatments effectively. Key phases in iron-carbon system of ferrite, austenite, and cementite. Ferrite is soft and ductile with low carbon solubility. Austenite forms at higher temperatures and dissolves more carbon, making it crucial for heat treatment. Cementite is hard and brittle, adding wear resistance. These phases combine to form microstructures like perlite, bainite, and martensite. Ferrite, alpha iron, is a body-centered cubic or BCC structure stable at low temperatures, soft and ductile, with very low carbon solubility. Austenite, gamma iron, is a face-centered cubic or FCC structure stable at higher temperatures, capable of dissolving more carbon, making it critical for heat treatment processes. Cementite, Fe3C, is an iron carbide compound that is hard and brittle, contributing to wear resistance. These phases combine in various proportions to form microstructures like perlite, bainite, and martensite, each offering distinct mechanical properties. Understanding these phases is essential for controlling steel behavior during thermal processing. Three key reactions occur: eutectoid, eutectic, and paratectic reactions. Eutectoid at 0.76% carbon and 727 degrees Celsius, eutectic at 4.3% carbon and 1147 degrees Celsius, and paratectic at 0.16% carbon and 1493 degrees Celsius. These transformations dictate microstructure evolution and mechanical properties. The eutectoid reaction occurs at 0.76% carbon and 727 degrees Celsius, where austenite transforms into perlite, a lamellar mixture of ferrite and cementite. The eutectic reaction happens at 4.3% carbon and 1147 degrees Celsius, where liquid solidifies into austenite and cementite simultaneously, typical in cast irons. The paratectic reaction occurs at 0.16% carbon and 1493 degrees Celsius, where liquid and delta ferrite combine to form austenite. These transformations dictate the microstructure evolution during cooling and heating, influencing mechanical properties. Heat treatment strategies leverage these reactions to achieve desired hardness, strength, and toughness in steels and cast irons. Microstructures and carbon content from ferrite to martensite. Microstructure development in steels depends on carbon content and cooling rate. Low-carbon steels predominantly form ferrite and perlite, offering ductility and toughness. Medium-carbon steels exhibit a mix of perlite and cementite, providing higher strength. High-carbon steels can form martensite upon rapid cooling, a hard and brittle phase ideal for wear resistance. Bainite, another microstructure, forms under intermediate cooling rates, balancing strength and toughness. These variations allow engineers to tailor properties for specific applications, from structural components requiring toughness to cutting tools demanding hardness. Heat treatments manipulate phase transformations. Annealing softens steel for machining, normalizing refines grain size, and hardening creates martensite for high hardness. Tempering reduces brittleness while retaining strength. Heat treatments manipulate the iron-carbon system to achieve desired properties. Annealing involves heating steel to austenite region and slow cooling, producing soft, ductile structures for machining. Normalizing heats steel above critical temperature followed by air cooling, refining grain size and improving toughness. Hardening requires rapid cooling, quenching, from austenite, forming martensite for high hardness. Subsequent tempering reduces brittleness while retaining strength. These processes rely on phase transformations predicted by the iron-carbon diagram, making it indispensable for metallurgical design and quality control. Effect on mechanical properties, strength, hardness, and ductility. Microstructure directly influences mechanical properties. Ferrite-rich structures are soft and ductile, suitable for forming operations. Perlite increases strength while maintaining moderate ductility. Martensite offers exceptional hardness and strength but is brittle, requiring tempering for practical use. Bainite provides a balance of toughness and hardness. By controlling carbon content and heat treatment, engineers can design steels for diverse applications, from automotive components needing impact resistance to cutting tools demanding wear resistance. The iron-carbon phase diagram serves as the foundation for these property optimizations. Time-temperature transformation or TTT diagrams show how cooling rate affects transformations. Rapid cooling forms martensite, while controlled cooling allows bainite or perlite. These diagrams help design heat treatments for desired properties. The TTT diagram complements the iron-carbon phase diagram by illustrating how cooling rate affects phase transformations. It shows the time required at specific temperatures for austenite to transform into perlite, bainite, or martensite. Rapid cooling bypasses perlite and bainite formation, resulting in martensite. Controlled cooling enables bainite formation for balanced properties. Understanding TTT diagrams is crucial for designing heat treatments that achieve desired microstructures and mechanical properties, ensuring performance consistency in industrial applications. Why the diagram matters in practice. The iron-carbon diagram is applied in automotive, construction, toolmaking, and foundry industries. It ensures optimal strength, toughness, and wear resistance in components. The iron-carbon phase diagram underpins countless industrial processes. Automotive manufacturers use it to design engine components with optimal strength and wear resistance. Construction industries rely on it for structural steels with high toughness. Toolmakers exploit martensitic transformations for cutting instruments. Foundries apply eutectic principles in cast iron production for excellent castability. By mastering this diagram, engineers can predict material behavior, reduce defects, and enhance product performance, making it a cornerstone of modern metallurgy and materials engineering. Summary and key takeaways of core concepts. The iron-carbon phase diagram explains phase changes in steels and cast irons. Key phases: ferrite, austenite, cementite, affect properties. Heat treatments and TTT diagrams help control microstructure for specific applications. The iron-carbon phase diagram is essential for understanding phase transformations in steels and cast irons. Key points include critical reactions, eutectoid, eutectic, peritectic, major phases, ferrite, austenite, cementite, and their influence on microstructure and properties. Heat treatments leverage these transformations to tailor strength, hardness, and ductility. Complementary tools like TTT diagrams refine control over cooling rates and resulting structures. Mastery of these concepts enables engineers to design materials for diverse applications, ensuring performance and reliability. Sources and further reading. Recommended references include ASM Handbook on Metallurgy, Callister's Materials Science and Engineering, and online resources from reputable metallurgical societies. These sources provide detailed explanations, diagrams, and case studies for deeper understanding of the iron-carbon system and its practical applications.